Okay, this is lecture 16. In the last lecture, we went over levers. In this one, we'll talk about the determinants of force production, and that's all we're going to talk about. There are 9 factors that we'll go through that account for the strength of your heaving. First up is neural recruitment. You know this stuff. You know all about size principle and how neurons are recruited. You know about GABA and its inhibition. You know about the Golgi tendon organ. You know about rate coding. That's all this is. The neural recruitment has a huge influence over skeletal muscle contraction. Remember, the bulk of strength improvement at the onset of an exercise program. That's all this is. Number 2 is cross-sectional area. It's not the mass of the muscle that matters, but it's the girth. If someone is 8 feet tall, right, they'll have really heavy muscles owing to length. Manute Bol weighed like 200 pounds, but that doesn't mean he was strong. He was like 7'7". I mean, he's really long, skinny muscles, right? Those don't produce much force. Thick muscles produce force, and that's what cross-sectional area is. It's a muscle that's packed with contractile proteins, which would do the contracting. Number 3 is the arrangement of the fibers. We talked about this before. There are lots of architectural styles, right? There's circular and parallel and pennate. The only two I'll draw attention to is parallel, the fibers that run in the same direction as the line of pull, and pennate, the angled fibers. Parallel and fusiform, these are weaker, but they're faster. Pennate, bipennate, multipennate, these are stronger but slower. This slide has a comparison of parallel to pennate. In parallel, it lists fusiform, like the biceps, and it also lists like circular, like sphincteral muscles, and flat, the abdominal muscles. In the pennate section, it divides them between unipennate, bi, and multipennate. Nothing surprising here, but it gives you some examples of the muscles that fit each architectural category. The fourth one is muscle length. Where are you in the range of motion? How elongated is the muscle? Which means how stretched out are your sarcomeres? And that sarcomere stretching affects the proportion of actin and myosin filaments that can interact. At rest, like in the midpoint of the range of motion, actin and myosin are in proximity to each other, and this facilitates a lot of cross-bridge cycling, cross-bridge binding, the formation of cross bridges. When they're contracted, when they're over-contracted, really contracted, the H zone disappears. That's where myosin is, but no actin is. So that space goes away, and this clumped up actin limits the number of available cross-bridge sites. And then when it's all stretched out, when the muscle's all stretched out, there are fewer myosin heads and actin binding sites in proximity to each other, so fewer potential cross-bridge sites are available. Now, remember the premise of variable resistance machines? These try to match the load placed on the muscle to the muscle's force capability throughout the length tension relationship. So it's attempting to make the moment arm of the load largest when the muscle is at its optimal length. This type of equipment has been studied, and this is one of those studies. They looked at 8 different leg extension machines, tested people isometrically and dynamically, and they had 10 male subjects. And the machines didn't do a very good job. Pretty much none of them effectively mapped their load onto the length tension relationship. None of them really did it well, which means the determinants of force production are going to be where you are in the range of motion, no matter what equipment you're using. But joint angle involves more than just the length tension relationship. So we're giving it its own category here. Number 5, joint angle. For starters, different muscles fire at different angles. Um, They're just different lines of pull. Like for a shoulder, the side raise, they're optimal angles where the deltoids can perform the action as opposed to the supraspinatus or other muscles. So that's what the image to the right is showing, the onset of when different muscles fire in a side raise. And there's a range of when particular muscles fire, but most shoulder muscles are going to be activated prior to the movement. But that doesn't mean they all have that, advantageous line of pull at the same time, whether it's early or in the middle or late. Mechanically, some muscles work better in particular ranges of motion or portions of a range of motion. Some muscles work better than others. And in individual muscles themselves, there are moment arm changes throughout the range of motion. So it's not just the length tension relationship that changes as you contract or extend. The moment arms change as well. It's a combination of both physiology, length tension relationship, actin myosin bonds, and physics, the changing moment arms. So if you look at the moment arm of the muscle here, um, the fulcrum, right, the elbow to the force, the tendon attachment and line of pull of the muscle. So that length, you see it changing throughout the range of motion, mirroring the length tension relationship. You have better mechanical leverage in the middle of the range of motion here too. But the moment arm of the load also changes throughout the range of motion. And the moment arm of the load can be seen in this diagram. It also reflects the length tension relationship. The longest moment arm of the load is experienced in the middle of the range of motion. And then this last concept within joint angle that I'll draw attention to is anatomical features like the patella have an effect. So what the patella is doing is increasing, it's lengthening the moment arm of the force. The diagrams here show the difference in that moment arm. So the moment arm of the muscle or the force with and without a patella, and it makes a difference. The quads have more leverage because of the patellar tendon. All right, number 6, muscle contraction velocity. This one, in the textbooks, it might be called the force velocity relationship or force velocity curve, but it's in all of the textbooks. It's a little bit silly, but I'll address it because it's all over the place in text. So what we're looking at here, we'll take the guy, right, who's bench pressing. I mean, weird placement of the 45s, in this diagram, sort of loosely thrown on the bar with nothing holding him in place. But if he's lifting a light load, he's going to be capable of moving the bar quickly. If he's lifting a heavy load, he's not capable of moving the bar quickly. And that's really all this principle is saying. At a maximum effort, a fast movement corresponds to a low force output, and a slow movement corresponds to a high force output. With a really heavy weight, you need tons of actin and myosin connected at the same time. So you're not cycling through them, crossbridge cycling as fast. If the weight is light, you don't need as many connections. So you can cycle through them more quickly. In other words, you can move a light thing quickly, but you can't move a heavy thing quickly. But the relationship, it isn't linear. Really heavy loads are going to fall at the same rate. If you're bench pressing 800 pounds or 2,000 pounds, those are going to crush you at the same velocity. Your resistance isn't doing anything. And the same is true for really light loads. We get 1 pound and half a pound are going to move at the same velocity. That extra half pound isn't going to slow you down like at all. So let's orient ourselves to the graph here. The curve represents the maximum possible contraction at a given velocity, or vice versa, the maximum velocity at a given load. The x-axis is speed, velocity, and then the y-axis is force. And where that y-axis touches x, that's zero velocity. That's no movement at all. It's an isometric hold. But if you go to the right, just a tiny bit of that, that's concentric. And you have a tiny bit of concentric velocity. That's the heaviest weight you can lift, so it barely moves. Go to the right a little bit more, and you have a little bit more concentric velocity, but the weight is a tiny bit lighter. Move to the right more, you have more velocity and a lighter weight, and so on. The same is true for moving to the left. That's just eccentric or eccentric velocity. Increase the weight beyond your 1 RM, beyond what you can hold steady in an isometric contraction, and the weight will slowly start to descend upon you. Increase the weight a little bit more, it'll drop faster. Like despite your best effort, increase it more, it'll drop faster. That's what this graph is showing. And a couple of additional things to notice is that maximum force will happen at your 1 RM, or like a 1 gram more than your 1 RM. So you can't quite move the weight, but you're exerting everything you have against it. That's the maximum force. The maximum velocity basically occurs while unloaded. But you can still accomplish it with really light loads. But the maximum amount of power, force times displacement. So force and velocity are both important here. The maximum power is right in the middle. It's a balance of force and velocity. That's where your maximum power is found. And that's what the graph on the right is showing. And then the graph on the left, you can see that trained muscle can maintain an elevated velocity at higher loads compared to that same muscle before training. Moving on to number 7. This one's obvious. Strength to mass ratio. I mean, it's like not obvious how the guy in back lights his cigarette, but the concept of power to weight ratio is easy to understand. So like I wrestled in middle school, and I wrestled someone once who didn't have legs. And like we were in the same weight class, so we weighed the exact same, and he didn't have legs. I mean, I still had like an enormous advantage because my body weight was distributed over 4 limbs, which is helpful. But you get where losses of body weight that don't affect performance, like maybe in a bench press competition, he would have been, more competitive. Um, so if there's a loss of body weight or reduction of body weight that doesn't impair your performance, that can change the nature of your performance. That, again, power to weight ratio. And then this one, number 8, is not obvious in the way that the last one was. There's a movie called The Internship with Owen Wilson and Vince Vaughn, and they interview at Google, and they're asked what used to be, apparently, this used to be a real Google interview question. And I'm assuming they've decommissioned it now that the movie has, spoiled the secret. But it was, okay, this is the question. You're shrunk to the height of a nickel and thrown into a blender. Your mass is reduced, right? But your density is the same. The blades start in 60 seconds. What do you do? I'll give you a couple of seconds to pause so you can think through it, or just maybe you've answered it already. But the answer is jump out. You just jump out. It'd be easy if you were that size. It's just a matter of scaling. Body mass increases much more rapidly than your functional mass does. And it's not just the result of like bones and organs and blood and carbs and water and fat and whatever weighing you down. Uh, I mean, like storage of elastic energy becomes more useful. Myosin is going to contract at the same velocity, but given constant body proportions, a smaller athlete is going to have a higher strength to mass ratio. And so this explains how a flea can leap like, I don't know, 200 times his body length or whatever. If you were to make it the size of a dog, it could leap an entire football field, except that it couldn't because it would then be the size of a dog. So its vertical jump and broad jump and all that would be just as unimpressive as a dog's because it wouldn't be tiny anymore. So cubes illustrate this phenomenon well. At twice the height, you have squared your volume, but you have cubed your mass. And so if you take those dimensions and scale it up from there, go from the flea, just take a flea and make it 10 times the height. And then also it would be 10 times the width and 10 times the thickness because It would no longer be a flea if it didn't scale in each of those dimensions evenly. Um, so 10 times taller means 1,000 times heavier, but its strength wouldn't increase anywhere near that much. So again, body size is not simple power to weight ratio. It's about the actual size of the creature. Smaller creatures have an advantage here, just obviously not in absolute strength. And then number 9, this is our last one, it's physiological explanations. We've spent considerable time on this one already. We'll spend a little bit more on it right at the end of the semester when we talk about physiological explanations for muscle fatigue, things like ADP to ATP ratio and phosphate accumulation, stuff like that. But just know that cross-bridge cycling can work optimally or it can work suboptimally, which makes it one of the explanations for force output. And that's it. That's all for lecture 16. This is the only question, right? Name the 9, and then in like one solid sentence or two pretty solid sentences, explain what each item is on that list. And I will see you in lecture 17, where we talk about joint compression and introduce the topic of injury.